From a distance, our galaxy would look something like this: a flat spiral some 100,000 light-years across, with pockets of gas, clouds of dust, and about 400 billion stars rotating around the galaxy's center. That center, bulging up and out of the galactic disk, is tightly packed with stars. Thick dust and blinding starlight have long obscured our vision into the mysterious inner regions of this so-called bulge. And yet, the clues have been piling up that something important, something strange, is going on in there. The first to take notice was the physicist Karl Jansky, back in the 1930s. He was asked by his employer, Bell Telephone Labs, to investigate sources of static that might interfere with what it saw as the killer app of its time: radio voice transmissions.
And besides these wire and wireless channels to distant places, long distance also means the art whereby the wires and wireless are brought together, stationed like sentinels in the telephone's conquest of time and space.
Using this ungainly radio receiver, Jansky methodically scanned the airwaves. He documented thunderstorms near and far, and another signal he could not explain. It sounded like steam, a hiss of radio noise. Jansky narrowed it to a spot in the constellation of Sagittarius, in the direction of the center of the galaxy. Located within a larger pattern of radio transmissions, Jansky's sighting would become known as Sagittarius A star. The word of Jansky's finding got out. He assured the public that it was not aliens seeking contact. But that's just about all anyone could say for over 3 decades. Then Eric Becklin got on the case.
Sagittarius rises right about there. First comes Scorpio around midnight, and then Sagittarius and the very big Milky Way, and the very core of the galaxy is right up there.
Becklin is one of those rare researchers whose curiosity and determination push our understanding to a whole new level. It was the 1960s, and astronomy, like society, was in a period of ferment. Startling new observations were being made, and new interpretations were in the air. Quasars had just been discovered, extremely bright beacons of light from deep space. Were they coming from the centers of distant galaxies? And what powerful objects were generating them? To study an event at the center of a galaxy, you have to locate it. Young Becklin first took aim at our neighboring galaxy, Andromeda. In ultraviolet light, you can see a dense glow in the middle. Becklin found the point where the light reaches peak intensity and marked it as the center. From our orientation in space, all of the Andromeda galaxy is in full view. But our galaxy is a different story. We live inside it, of course. Becklin had to find a way to see through all the dust and gas that obscure our line of sight into the center. So he went to a military contractor and obtained a device that reads infrared light, whose wavelengths are similar to the distances between particles in a dust cloud, allowing them to move right through. Becklin began measuring the brightness of the light as it rose to a peak, marking the location of the galactic center. Pinpointing this site would now allow astronomers to begin probing for details, with a new generation of powerful telescopes, to peer into the bright lights, the forbidden zones, deep in the heart of the Milky Way. Becklin wasn't the only astronomer interested in the galactic center.
Now, you see these little sets of little images on the right side.
Reinhard Genzel and a team based at the Max Planck Institute for Extraterrestrial Physics in Germany began a similar campaign in 1990 from the New Technology Telescope in the mountains of Chile. A few years later, in 1993, high atop Hawaii's Mauna Kea volcano, Eric Becklin and colleagues, including Andrea Ghez, began using the newly christened Keck telescope. The American and German groups shared the same goal: to pinpoint the precise location of Sagittarius A star and to find out what it is. Because the object is too small to see at 26,000 light-years away, they would study it by tracking the orbits of stars around it. Even seeing them would take the sensitivity of Keck's wide aperture, an instrument powerful enough to detect a single candle flame at the distance of the Moon. Meanwhile, using a similar technique, astronomers had focused the new Hubble Space Telescope on a different galaxy, a giant elliptical cloud of nearly 1 billion stars lying some 50 million light-years away, called M87. They tracked gas whipping around its center, figuring its speed at 3 million miles per hour, which led them to calculate the mass of whatever occupied M87's center at some 4 billion times that of our Sun. Their measurement, the first ever of its kind, pointed to the presence of a black hole of truly supermassive proportions. But it didn't conclusively prove its existence. Back on Earth, the German and American teams each hoped that the proximity of the Milky Way's center would allow them to look through the curtains of swirling gas clouds into the monster's lair, to conclusively prove, for the first time, the existence of supermassive black holes. This search was part of a larger effort to unravel the complex terrain of the galactic center, in search of clues to the origins and evolution of our galaxy. Recently, using Hubble, astronomers documented vast arcs of gas heated up by ferocious winds from large stars. Capturing infrared light, the Spitzer Space Telescope picked up the pervasive swirling heat signatures of all these stars. The Chandra X-ray Space Observatory recorded high-energy radiation, most likely given off by ultra-dense neutron stars and small black holes. Scientists estimate that a swarm of 20,000 black holes inhabits the inner 3 light-years of the galactic center. If there is a supermassive black hole at the center of it all, the teams would have to show that it's confined to a very small volume, and that it has enough gravity to whip the stars orbiting it to high speeds. The light of these stars travels 26,000 light-years to reach us, only to be blurred in the last few miles as it hits Earth's atmosphere. So both teams turn to a method designed to sharpen it back up. The idea is to snap thousands of pictures in a short time. Because the atmosphere is in motion, a star's apparent position may shift from image to image. To hone in on the star's true location, a computer averages the positions and looks for correlations in the wavelengths of the star's light. Here are the stars they began tracking, clustered around the center of the galaxy. The first few years' data allowed the teams to calculate the speeds of the stars and their rough trajectories around the center. That allowed them to pinpoint the position of their target, as well as its gravitational pull.
Well, if you're going to center here and go 6...
And that gave them its mass, roughly 3 million times that of our Sun. Because no other single object is known to weigh that much. It's strong evidence of a black hole. But it's still not ironclad proof. These data, for example, don't rule out a dense concentration of stars packed into the center. held there by their mutual gravity. The proof the teams sought would have to wait for an extraordinary event. In the early years of this new century, large telescopes around the world began to install upgrades. Most large new telescope mirrors these days are thin, designed to be mounted on metal scaffolding. Behind the mirrors, engineers install pistons and motors to subtly correct the shape of the glass as changing temperatures deform it, or as atmospheric turbulence blurs the incoming light. Some have added lasers, designed to project an artificial star onto the upper atmosphere. As turbulence causes its light to distort, a computer can use it to subtract the net effect of that turbulence from the light of the real stars, bringing them back into focus. This is a Keck image of the galactic center, without adaptive optics applied. And with them. With this increase in sharpness, the teams were ready for what happened in 2002. The German team had begun making observations at the new Very Large Telescope array at the Paranal Observatory in northern Chile. In the spring of that year, one of the stars they had been following, known as S2, made a dramatic move. S2 suddenly swooped around the center, accelerating to around 3 million kilometers per hour. The American team saw it too. It had come incredibly close to the suspected black hole. If there had been a cluster of stars in there, S2's path and its light would have wobbled. It did not. This was the evidence the teams had sought. It showed that Sagittarius A star is a single object, without doubt, a black hole. You can argue whether that's definitive proof, but it's nothing short of spectacular. This observation came at a time when astronomers had begun to believe that black holes play an active role in the evolution of the universe. They had found that giant black holes occupy the centers of nearly every large galaxy. In fact, the larger the galaxy, the larger the black hole. That suggests that the two must have evolved hand in hand, each shaping the life story of the other. As matter flows into a black hole, it heats up to millions of degrees. Despite the black hole's intense gravity, much of the inflowing matter blows off in fierce winds and in powerful jets, roaring out of its poles. The more matter that rushes in, the more the black hole pushes back out. The force and the heat from active black hole outbursts can have the effect of limiting a galaxy's growth by putting an end to starbirth, and also pushing loose gas out of its central region. This has been going on since the earliest days of galaxy formation. One result, a strict relationship has developed between the size of the black hole and the size of the galactic bulge that surrounds it. Here, in our Milky Way galaxy, is our own supermassive black hole still growing and still shaping its galactic surroundings? Just as the black hole Sagittarius A star finally revealed its existence, it would now show its true colors. The year 2001. Scientists were working to commission the newly launched Chandra X-ray Space Telescope. They pointed the telescope at Sagittarius A star, and by chance, at that moment, it erupted. The teams on the ground began focusing on it for longer periods, hoping to see it happen again. And so they did. They saw what's now thought to be flares, outbursts that erupt when matter builds up near the event horizon before falling into it. A group of astronomers is now making plans to get an even closer look at these flares, and, for the first time ever, to directly glimpse a black hole. To date, no single telescope on Earth has enough resolution to see something so small, so far away. But radio astronomers think they have a way. By linking observatories around the world, they can create what amounts to an Earth-sized radio telescope. This simulation shows what they expect to see just a few years from now. A supermassive black hole in silhouette, framed by eruptions on its surface that travel around the monster as it spins. Perhaps images like these will shed light on a particular mystery. The flares appear to be very weak, considering the amount of matter swirling around the galactic center. What these flares seem to be showing us is that our black hole and our galaxy have settled into a period of semi-retirement. But they are bound to become active again. Observing with the Very Large Telescope in Chile, astronomers recently picked out a straggler from the intergalactic wars of old. They spotted, deep in the recesses of the galactic center, what's left of a smaller galaxy that had been torn apart by the gravity of the Milky Way. This group of stars is so densely packed that it's able to survive the tidal forces around it. Eventually, it will find its way into the galactic center, where its doom awaits. Most likely, it will be swept into the torrent of gas and dust and stars destined for the mouth of the monster. Working in the cold, clear, dry air of Antarctica, one group of radio astronomers has tried to find out when the Milky Way's central black hole will begin feasting again. Data from their South Pole telescope has delivered signs of a disaster in the making. A huge ring of gas looms beyond the galactic center. When it accumulates some 300 million suns worth of matter, it will reach a tipping point. The cloud will begin to funnel into a second ring that orbits close to the center. This inner ring will condense, then erupt with star formation, before spiraling down toward the ravenous black hole. As the cloud falls into it, the black hole too will erupt in a blaze of glory visible across much of the universe. Based on these findings, the thinking is that outbursts like this repeat every 400 million years or so. Meanwhile, on one rocky outpost, a safe 26,000 light-years from the turmoil at the center of the galaxy, curiosity continues to reign. We have found ways to track the patterns of change over billions of years that have shaped our universe. And yet, sometimes, it's the small events that feed our sense of wonder. Take the star called S2, speeding around the black hole Sagittarius A star. In 2008, it made its way back to the exact same spot where astronomers had begun tracking it. That was the first time any object has been seen making a complete orbit around the center of the Milky Way. What will happen over the course of its next orbit? No doubt we'll answer many of the questions raised by this star and the supermassive companion that whips it around. Along the way, we're sure to see things we don't yet understand, that raise questions we cannot yet answer.